Hi, Hugh. We are online and ready to go when you are.
Okay, well, I'd like to welcome you to the 14th virtual symposium on CH functionalization. Those of you are here now are very virtuous because you're going to listen to some great science instead of watching World Cup soccer. So good for you. It's only England and some other team playing, so who cares anyway, coming from Wales. Okay, you know, this has been an event we've had now for the last 3 years. And what I want to do, first of all, is to discuss a little bit about the housekeeping with the meeting. If I could have the next slide, Dan. So, first of all, with regard to questions, I believe this link is not working. I think if you have questions, you need to come through Twitter, so with CCHF, Twitter to NSF CCHF, if you have any questions coming up in the meeting. We have 3 speakers. The talks will be for about 20-25 minutes each with some time for questions. If you're with a group, we would really appreciate if you could take a picture and take a photo of your group and please send them to us. Those of you who have been at these meetings before know that Ken Hauk is the expert at doing selfies, but we want to have some serious competition, so please send us your photos of your group as well. And then it's always good for us to get feedback about how you think the meetings proceed. We have made some changes. We used to have 4 speakers, that went on a little bit too long. So now we've changed it to 3 speakers. And we're always interested in your views about how to make this meeting better. Okay, next slide, please. So the reason why we started these virtual symposia was because we had a big problem in the Center for Selective CH Functionalization, where we had professors from 15 universities working together and needing to find a very effective way of large-scale communication. And having succeeded in being able to do that, we thought, well, wouldn't it be great to be able to communicate broadly across the world the excitement of CH functionalization? And this is indeed what we've been able to do. And the reason we've been able to do that, if I can have the next slide, well, just to illustrate, just to illustrate how this works. So you can see people come from lecture halls and conference rooms from within the US, also from many countries across the world. And as a live event, we have people coming in from Korea at 5 o'clock in the morning, from Japan at 5 in the morning, from Europe at around 9 or 10 o'clock in the evening. So all different times, and it's just been great to see such engagement from across the world. Now, the reason we've been able to do this is shown on the next slide, is really because of the amazing technical support that Dan Morton has been, first of all, understanding how to get the whole center to be able to communicate really effectively, and then running these meetings that involves quite a challenge, because these meetings are sent out by Zoom as well as by YouTube simultaneously. So it's quite a challenge to bring all of this together. It's been phenomenal what he's been able to achieve. Indeed, this is a great time for me to actually thank Dan for all of the work he's done for the center, because actually he's going to move on to a really exciting new job involving a program involving the Gates Foundation. And so while we congratulate Dan on this exciting new opportunity, we also want to thank him for the incredible job he has done for the center. And by the way, if anyone knows of any other Dan out there, we will be looking for that person. So if you know someone who's really passionate about science, but also is really interested in this type of communication and managing a broad center like this, please send me an email. I'd love to hear about that person. Dan's going to be a tough act to follow. Okay, next slide, please. But if anything could follow, Dan, is this amazing selection of speakers we have to finish off the program. So we've got a really interesting mix. We've really got an interesting mix of thinking about synthetic strategy as it relates to CH functionalization, new reactions, free radical chemistry for doing CH functionalization, and then the amazing possibilities in terms of using enzymes to not only enhance natural reactions in nature, but actually totally unnatural reactions. There's a huge impact on CH functionalization. So we're really delighted to have Richmond Sarpong from Berkeley, Eric Alexanian from University of North Carolina, and Francis Arnold from Caltech to be willing to present to us today. Okay, so the first speaker is going to be Richmond Sarpong. He's been a member of the center now for an extended period of time, since the inception of the phase 2, and really has been a thought leader in terms of thinking strategically and in terms of how to use CH functionalization. So Richmond, we're very much looking forward to your talk.
Okay, thank you very much, Hugh. It's a real pleasure to be part of this 14th edition of the CCHF Virtual Symposia. It's really my pleasure to present on behalf of my coworkers here at Berkeley. And today I thought I would tell you one story, but this story will be placed in the context of our involvement in the center. And so I think all of us can agree that organic synthesis, at least as we think about it, probably began in 1828 with Friedrich Wohler's urea synthesis. And it's almost been 200 years since that time. And I think as we advance to 2028, a lot of us can agree on some of the directions that the field is going in, but perhaps there are new directions that would emerge as well. But certainly, I think all of us adhere to the fact that this inception of synthetic organic chemistry really began with the CN bond formation in the synthesis of urea by Wohler. However, in the ensuing 190 years or so, the field has really been driven by carbon-carbon bond formation. And of course, this is primarily due to the fact that a lot of the targets that one looks to address with organic synthesis are really based on a carbon framework. And so carbon-carbon bond formation has really formed the basis for advancing the field. And here are some examples of the types of target molecules that one can address using carbon-carbon bond formation primarily. But of course, carbon-carbon bond cleavage is also an important aspect of synthetic organic chemistry. And so here I show a few examples of the types of carbon-carbon bond break-in reactions that have been part and parcel of synthetic organic chemistry. And most of these are attended by a bond-forming process as well. And by far, the most sort of historically relevant carbon-carbon bond cleavage reactions in organic chemistry have to do with cases where you have either a functional group that's proximal to the bond that's being cleaved, or a latent functional group, for example, a double bond being proximal to the bond that is being cleaved. And so we asked the question whether there's any value in cleaving carbon-carbon bonds in a general way, even in cases that might be devoid of the sort of traditional functional groups that we think about. And of course, a lot of this is inspired and driven by lessons from sort of the state of the art when it came to thinking about carbon-hydrogen bond cleavage and functionalization. And so in a classic example, one can think perhaps of the deprotonation of a carbonyl compound at the alpha position as an example of a CH cleavage in the traditional sense. And of course, this then is followed by a bond-forming process where an electrophile is introduced. But the field of CH functionalization is, of course, advanced tremendously. And here are a few examples of the types of CH of cleavage reactions that are then followed by bond-forming processes that now can be affected even in the absence of a traditional functional group being proximal to the CH bond that is cleaved. And of course, is the work of Hugh Davies, and this has been one of the fulcrums of the Center for CH Functionalization. Now, my group has been involved in the center, as Hugh mentioned, for some time, and our charge as part of the center was to really think about ways in which we could apply CH functionalization methods to address the synthesis of complex molecules. And so on this slide, I show some examples of the types of bond-forming processes, which are highlighted in red, which were really inspired by thinking about CH functionalization. And in general, these bond-forming processes or CH cleavage processes that are then followed by bond-forming were really driven by thinking about CH functionalization in two ways. And so for the two examples that I show here, I would say that our idea was that we could affect perhaps a peripheral functionalization of a molecule, such as the left-hand portion of this compound, complandin A, at the periphery of the molecule, which then would enable us to affect a CC bond-forming reaction to bring the two halves of this molecule together. Alternatively, for this molecule, my branchiamide C, we thought about a peripheral functionalization site selectively at the C6 position of the indole that would then set the stage for us to install the chromine that is found in a molecule like YKLoid A and go on to build molecules of that type. So this is a type of CH functionalization that I refer to as a peripheral functionalization, where we're thinking about functionalizing the molecule on the periphery. The other type of CH functionalization that we thought really benefited complex molecule synthesis was one that I would term core functionalizations, where we would forge a CH bond, we'll cleave a CH bond to forge a new bond that would form part of the core framework of the molecule. And so, for example, here the idea was to effect ultimately a CN bond formation by cleaving a CH bond that resided at this position. And the same was also true here in the context of this molecule, where a CH bond would be cleaved to ultimately forge a carbon-nitrogen bond. And as we thought more about these ideas of cleaving CH bonds to forge other bonds, and especially in thinking about this in the context of late-stage functionalization, we wanted to think about ways in which one could achieve maximal diversification of molecules at a late stage. And of course, peripheral functionalizations have been utilized extensively for this purpose, but we also wanted to think about ways in which one could do this at the core of organic molecules, and that would necessarily mean thinking about ways in which one could break carbon-carbon bonds to forge new bonds. And so the idea that we had was really what we call tongue-in-cheek, our break it to make it moment, which is this idea that perhaps just as we've been thinking about CH bonds as functional groups, could we now start to think about carbon-carbon bonds in the same vein? And so I thought I would begin by illustrating this in the context of one total synthesis that we've undertaken in my group, which is a total synthesis of a molecule called formactin A. And this is a molecule that is a member of a larger family of diterpenoids, which were isolated initially from the backs of a snow crab found off the coast of Okinawa in Japan. So the fungus that produces these secondary metabolites resides in a symbiotic way on the backs of these snow crabs. And these molecules are interesting from a structural standpoint, as depicted here by formactin A, but there's some emergent interest in these molecules in terms of their function as platelet activating factor receptor antagonists. And that, of course, has a lot of implications in terms of thinking about diseases that have to do with inflammation, such as cardiovascular disease, cancer, and so forth. And so we were interested in the synthesis of these molecules, first, obviously, to address the challenge of their complexity and how one can address that with a chemical synthesis, but ultimately with an eye toward also bringing perhaps some insight into the function of these molecules. And so as we considered the family as a whole of the formactins, what we came to appreciate is that all the congeners in the family actually have the same carbon skeleton, which is depicted here in this blue rectangle. And one thing that seemed to be the case is that if one thought about biosynthetically how these molecules arise, it may be the case that a late stage P450 sort of tailoring mechanism would account for how oxygenation is achieved in all of these molecules. And so we worked with an isolation chemist, actually, because we thought that there must be opportunities for other types of oxygenations. And so working with Professor Roberto Berlink from Brazil, we were able to isolate additional members of this family, which indeed also had the same carbon skeleton, but differed in terms of the oxygenation. And so we were confident that if we could identify a common carbon framework, we could then perhaps achieve diversifying oxygenation at a late stage to build these molecules. And so that led us to identifying this particular compound in the bottom right as a common synthetic intermediate that we could apply to address the syntheses of all the formactants. So I'll fast forward and just sort of give you a bit of an overview of the existing syntheses at the time that we began our work. Several groups have indeed achieved syntheses of individual members of the formactant family. I note some of these contributions here, and these are nicely summarized in a review by Alison Frontier's laboratory. And the gist, at least in terms of the syntheses that produce material in an enantiomer-enriched form, is that there was a lot of steps that were invested in building what I would call the cyclohexene portion of these molecules, which is a 6-membered ring which resides here in the framework of formactant A. And so we thought if we were going to make any contributions in an impactful way to the synthesis of these molecules, we had to find a way to achieve the synthesis of this portion of these molecules in a shorter step count. And so our idea was that our common synthetic intermediate that we had identified could be brought back to these two fragments. The vinyl iodide had been utilized by Yamada in his group synthesis of the formactants, and so that we would borrow in terms of how to prepare that, and really the contribution that we're going to make really rested on our ability to prepare a cyclohexene fragment of the type shown here. And that we thought we could bring back to a precursor such as this compound here, carbone, which is readily available. Either an enantiomer can be obtained in metric ton scale. And so we thought that would be a great starting point to address the cyclohexene fragment. And so the key question then became how we advance carbone to this particular fragment. And so in that regard, we thought that if we start from carbone and we're able to build a bond between this blue dot and this blue dot, that would enable us to forge the CC bond that I showed here. And so that would then lead to a tetrahedral intermediate. And our idea then was to cleave this carbon-carbon bond in that tetrahedral intermediate. And of course, because carbanions are bad leaving groups and not great leaving groups, we thought we would do this with the sort of assistance of transition metal catalysis. And so I wouldn't go through this in detail here, only to say that, of course, pi bond activation, one can readily achieve. CH bond activation is much more challenging because of the orientation of the CH bond sort of orthogonal to the d orbital system of the metals. But of course, due to the s orbital of the hydrogen, one can now arrive at an agostic interaction that ultimately leads to activation of the CH bond. A CC bond activation, on the other hand, becomes even more challenging because the d orbitals have to become proximal to the sigma bond for the CC bond. And of course, each of these carbons bears substituents that makes it difficult to achieve that level of proximity. Now, our field has contributed tremendously to ways to think about CH bond activation. And so here I list some of the current leaders in this area. And I think a lot of the insight that's been brought to this is that if one can actually constrain a carbon-carbon bond in a small ring, you can achieve a rehybridization of that sigma bond. And so, for example, in cyclopropane, we can think about the Walsh orbitals that arise where there's more emergent p character to that carbon-carbon bond. And so kinetically, that now makes it possible to have a more pronounced interaction with the d orbitals of the transition metal. And so that's a kinetic argument. On the thermodynamic side of things, of course, carbon-carbon bonds are strong bonds, whereas in many cases, carbon-metal bonds are relatively weaker bonds. And so if you can associate the cleavage of the carbon-carbon bond with a strain release, such as that which is achieved in cleaving as cyclopropane, that can enable one to ultimately arrive at either a thermoneutral process or perhaps even an exergonic process. And so that was our idea then, was to adopt this plan to introduce strain into the carbon-carbon bond that we're seeking to cleave. And so we could take carbone, epoxidize this isopropenyl group, effect a reductive CC bond formation with opening of that epoxide, which proceeds through transition states that are sort of depicted here in cartoon form, ultimately leading to these two bridged diols. And so these look somewhat esoteric, but in fact, these are simply hydroxylated versions of pinene. And so if one were able to site selectively hydroxylate pinene, you would arrive at these compounds. But of course, pinene hydroxylates at the allylic positions, which are much more activated, to give verbinol and myrtenol. And so this is sort of a roundabout way to get to these particular hydroxylated pinenes. And so with those compounds in hand, which are now, of course, bear the inherent strain of the bicycle and also the cyclobutanol, we could affect cross-coupling reactions that now involve cleaving the carbon-carbon bond. And so, for example, in this particular instance, we could start with an oxidative addition into this carbon-halogen bond that then is followed by a ligand exchange onto the tertiary hydroxy group, and then a beta carbon elimination proceeding through the sort of four-center transition state, ultimately terminating with a reductive elimination would lead to this particular compound. On the other hand, if one uses a rhodium complex, one can terminate with a protonation event to arrive at this particular compound shown here. And so in that way, we can now achieve sort of a rearrangement of that particular skeleton where we subsume this isopropenyl group into the ring and release this methylene as a methyl group through 4 steps to now arrive at this compound that I show here on the right, via the intermediacy, of course, of the cyclobutanol through the process that I just showed on the previous slide. And so following a sequence of steps, which described here, I won't go through this in detail, we could prepare our common synthetic intermediate in a total of 16 steps. And with that common synthetic intermediate in hand, we could now drive a series of oxygenations using the secondary hydroxy group to direct those oxygenation events. And so, for example, directed now vanadium mediated epoxidation at low temperature affords in this particular epoxide, and then oxidation of the secondary hydroxy group affords formactin R. One could then effect an epoxidation of this more distal double bond to afford formactin P, and an allylic oxygenation then affords formactin K. If one carries out that epoxidation at a slightly warmer temperature of 0 degrees Celsius, one can effect a double epoxidation, and this then enables us to get to all the other formactin family members that represents the structures of the formactins in 20 steps or less for the whole family. And so we've now taken this idea of CC bond cleavage by the intermediacy of the strained rings and applied it to the synthesis of other molecules. And so, for example, one can begin with carbone, take that on to the cyclobutanol shown here, and utilize this now to drive a palladium-2 mediated CC bond cleavage, CC bond formation cascade, ultimately leading to this bridged tricycle, which then has been taken on to a synthesis of this molecule, isocyanopropanone, in our laboratory, and work led by Melissa Hardy and group. Alternatively, one can advance carbone to this bridged bicycle, again bearing a cyclobutanol, and effect a cascade process where we cleave the CC bond to forge now a new CC bond, and ultimately take that on to molecules in the Jijicorin family of molecules. And in one emergent example from our group that we're very excited about, in work led by Brian Wong in the laboratory, we can take carbone and advance it to these 2 fragments, and then bring them back together again through a CC bond cleaving, CC bond forming reaction, and then finish off with an aldol reaction to prepare the core structure of the taxoid molecules in a total of 15 steps, longest linear sequence to get here, And we're now at the stage where we're completing the sort of site-selective oxygenations to finish this off. We've been able to achieve each of these oxygenations individually, and we're now sequencing them to finish off molecules such as taxajophene. And so the question is often asked how we can perhaps take some of these ideas and move them on to apply to what many would term pharmaceutically more relevant systems. And so to me, this is a bit of a question that I really never really understood, and so decided to delve a little bit deeper into understanding what a pharmaceutically relevant system would be. And of course, if one takes a look at sort of the existing table of the most prevalent heterocycles in pharmaceuticals, the piperidine emerges, and again, this is borrowed from a table from Jon Yardison's laboratory. And this is for good reason, because if one looks at a number of the pharmaceutically relevant molecules out in the market, you quickly come to appreciate that the ability to have a piperidine ring, which is then substituted with various substituents, can now lead to a range of activity. And so in general, there's been a lot of interest in being able to program the site-selective functionalization of piperidines in a controlled way. Now, of course, this is not a new idea, and this is an idea that many have thought about before. Our laboratory has become interested in this, and if one looks historically about at how this has been done, one only needs to look at the work of, for example, Peter Beek or Gideon Frankel and others that have contributed to this area, Bob Gawley and so forth, to appreciate that in the past, really a big push in being able to functionalize piperidines was to utilize, for example, a Bach carbamate to direct a lithiation event. And then at that stage, one can envision a transmetallation, for example, to a Negishi precursor nucleophile. And then you can carry out the Negishi type cross couplings to your heart's content. Okay, and more recently, contributors to this area include Ian Coldham, Paul Nochel, and Olivier Baudouin. Of course, in this center, there have been a lot of contributions, given the fact that these types of lithiation events are strongly basic and there's less of a functional group tolerance. There's been a real interest in being able to do this under functional group tolerant conditions, and also to essentially couple the steps of activating the position alpha to the nitrogen and also affecting the cross-coupling. And so this can now be achieved with a range of different metal complexes in the CH functionalization process. This is a very powerful way to now functionalize molecules. Of course, Jin Kwon Yu within the CCHF has been a major player in this area, and there have been, in fact, many other players, such as those that I list here. Now, we became interested in being able to essentially benefit from these existing precedent to think about ways in which perhaps we could also start to achieve these types of CH functionalization cross-coupling processes. Now, we were especially drawn to this type of lithiation event because one of the things that I came to appreciate in a lot of conversations with folks from industry is that they kind of liked the idea of forming, for example, the initial organozinc because a lot of the cross-coupling reactions that were then carried out subsequently utilize the same set of conditions. And so by dissociating the initial nucleophile formation from the cross-coupling, one could arrive at a common intermediate that you can use to diversify in terms of the cross-coupling with not only aryl halides, but perhaps even alkynyl or alkenyl halides. And so sort of taking a bit of a lesson from that, we really wanted to identify a way in which we could arrive, if you will, under very mild conditions at a functional equivalent to this organolithium. And so we thought that we could begin with these sort of photoreactive keto amides, which under visible light conditions, we could affect what would be a Norrish-Yang process to arrive then at these alpha-hydroxy beta-lactams. And this then will serve as a functional equivalent to a species of that type. And so one could then imagine cross-coupling reactions where we would affect CC bond cleavage cross-coupling to either achieve an arylation, alkynylation, or vinylation. Now, on paper, this process looked reasonable and straightforward, but of course, these types of pursuits are marred with complications. And so we entered into a very fruitful collaboration with Merck Research Laboratories, working with Dr. Charles Young, who's a Merck Disruptive Chemistry Fellow. There's a program at Merck. And Charles has really led our efforts to really utilize high throughput experimentation screens to really identify the best catalyst to achieve this particular process. And to give you a bit of insight as to why we needed to identify the best catalyst, I have to tell you a little bit about how we think about a catalytic cycle for this process. And so presumably we begin with an oxidative addition to our halide, and then a ligand exchange onto this tertiary hydroxy group. And at this state, one can envision either a beta carbon elimination to cleave this bond here, which we would term proximal to this ring, or to cleave this bond, which we will term distal to the ring. And so it turns out, depending on the choice of ligand on palladium or even the metal, one can drive this toward the proximal cleavage or the distal cleavage. And ultimately, for our purposes, we wanted the proximal cleavage. And so we've screened a number of complexes and ultimately arrived at this Rufus palladium G4 as the best complex to enable us to arrive then at the cross-coupling at the alpha position. And so we've looked at the substrate scope for this extensively and identified that we can cross-couple in general the piperidine ring systems. We can also achieve the cross-couplings with morpholines, as well as azopanes and azocanes. And these cross-couplings can even be conducted in the presence of acidic groups such as this NH group or the position alpha to the cyano group. We've looked at this for vinylation as well. Here I show one example. The yield is not the highest, but it really just illustrates this idea that one can effect the cross-coupling and then have that follow with a Prince type cyclization, ultimately leading to bicycles of the type shown here. And so as we moved from arylation to alkynylation, then to alkynylation, we had a little bit of a surprise, which is that starting from this beta hydroxy, this alpha hydroxy beta lactam, and looking at the alkynylations, we actually got a product which is the beta functionalized compound. And when we looked at this in the azopane series, what we saw was the double bond product shown here, this sort of enamide product, as well as the alpha alkynylated product. And mechanistically, when we think about this, we imagine that these products might be arising from the same type of organopalladium intermediate that I'm circling here, but instead of undergoing a reductive elimination to lead to the alpha functionalized products, perhaps what ensues here is a beta hydride elimination, and the palladium hydride will still be bound eta 2 to this double bond and can reinsert as shown here, and reductive elimination at this stage will then lead to products such as this alkynylated compound shown here. And of course, the beta hydride elimination dissociation would then lead to these types of enamides. Now, this is not a new process. In fact, Oliver Baudouin's laboratory has recently identified a very nice ligand to enable one to do this from the organozinc intermediates. And this is work that was initially reported by Paul Noschel's laboratory. And so there are ways in which one can drive the beta functionalization with ligands, but of course, there's also an interplay between the ligands and the cross-coupling partner. And so what we found is that indeed the cross-coupling partner can overwhelm this process, but of course, ligands can also drive this process as well. And so we've been looking at ways in which we can use ligands to drive these processes, not only for the alkynylation, but also for arylation. And so in an early example, using this pyrrolidinone, we can now start to achieve both alpha and beta and start to change the ratios for these two products of arise. Now, the cross-coupling reactions we've been looking at are relatively mild. We can conduct these in the presence of diazurines, and this now becomes important as one thinks about bioconjugation strategies. One can do these for relatively complex precursor compounds such as steroids. And in one complex example, we can utilize these sort of stoichiometrically generated organopalladium intermediates reported by the Merck laboratories and Steve Buchwald's laboratory to now effect these types of cross-couplings as well. And then finally, we've also shown that one can carry these out in a stereospecific way. These reactions proceed with a stereoretentive cross-coupling to arrive at for example, this arylated product. And so just to recap where we are, we're very much interested in this idea of a programmed way to functionalize piperidines and other saturated azide heterocycles. And thus far, we've been very interested in the idea of alpha functionalization. We envision that perhaps we can now sequence these types of functionalizations to achieve a second functionalization. We can also, perhaps with ligand control, enable us to then achieve a beta functionalization as well to arrive at this group of products. And so this is work, this is very much aspirational. It's work that's ongoing. We have not so far been able to achieve functionalization at what I would term the 4 position of the piperidine. However, Hugh Davis's laboratory has a very, very powerful way to do this. And so we're actually in a collaboration with the Davies laboratory. Wenbin Liu and the group has been working with Justin Jurzik in our laboratory and also with the Merck Research Laboratories to look at this in detail. And so this is very much aspirational, kind of where we're headed. But of course, why stop here? And so if you can do this, why not think about ways in which one can continue to sequence and program how we introduce different substituents on these piperidines. And so we hope that these keto amides will now serve as groups that will enable us to do this in an iterative way. And ultimately, these are groups that we can cleave under relatively straightforward conditions. All right, so that's the story I wanted to share with you today. Again, my laboratory is very much interested in complex molecule synthesis, and we think primarily about strategy and how we can employ different methods to build complex molecules. More recently, we've become very interested in this idea of merging CH functionalization with CC bond cleavage reactions, and we think these present new opportunities for not only building complex molecules, but perhaps also accessing at a late stage a diverse range of pharmaceutically relevant compounds. And so what remains for me to do is to thank the people who've done the work. I'm really indebted to my research group and also the current support that we have. The NSF Center for CH Functionalization, of course, is to be thanked, as well as Merck Research Laboratories for the work that I presented here today. And specifically with the work I presented, the people that have led the way, Jose Roque and the laboratory's graduate student, Dr. Yusuke Kuroda, Justin Jurzik, these have been the primary players on this work. Lucas Gottman, Karis Roberts was a CCHF summer student that came in and made quite an impact on the group on this work. And of course, our collaborators at Merck have also been great. Dr. Charles Young has really driven not only the HTE work that I talked about, but many of the intellectual directions that we've taken a number of the project directions in the group. And then finally, none of this would be possible without the CCHF. As Hugh mentioned, this is an incredible organization that really fosters innovative thinking. And we have a number of collaborations here. I gave one of these virtual symposia talks before, and I talked about some of our other work. And so I thought I would talk about some of the newer work today. But Professor Jamal Musayev, Professor Jin-Kwon Yu, and Professor Davis have been key collaborators, as well as Professor David Sherman from the University of Michigan. And so finally, I'll stop there and thank you for your attention. And I'll be more than happy to answer questions. Thank you very much.
Very nice, Richmond. A very elegant talk all around. We're running a little bit tight on time, so it's just one question for you at this stage. So your ring openings have been done with 4-membered rings, and obviously you've got some lovely examples of using it. So 3-membered rings would presumably do it even faster. Are there any synthetic possibilities there? And also with a 5-membered ring, even though you haven't got the ring strain advantage, is it possible to use really forcing conditions and get 5-member rings to operate, either microwave or something like that.
Absolutely. So you raise very good points. And in fact, I'll mention that there is one example of a 5-member ring opening with rhodium. And this is work done by Nikolai Krama's laboratory. Of course, this is in the context of sort of a Norbornane system. So there's the inherent strain that is resident in that system of about 21 kcals per mole spread across those 7 carbons. But I think these are all possibilities. Certainly the 3-membered rings, this has been looked at extensively. More recently, I can think of Art Oriana in Canada's looked at some of the work in that regard. For us, the important thing has been ways in which we can generate the strained ring system under relatively mild conditions to enable us to carry out these processes. And so we've sort of focused in on that. We've found that the 4-membered rings provide several opportunities. But of course, we are thinking about larger rings like 5-membered rings and even beyond. And so, I didn't talk about it today, but we are interested in not only sort of transition metal beta carbon elimination processes, but even thinking about, beta carbon-carbon bond cleavage events, sort of radical processes. And so we've reported a couple of examples of those in the context of using silver to drive some of these processes. We have some emergent examples with copper as well, which we hope will be in the literature soon. And so, yes, we are thinking broadly beyond just the 4-membered rings.
Okay, great. Well, once again, thank you very much, Richmond. Okay, our next speaker is Eric Alexanian, who's from UNC Chapel Hill. And as I said, this is people come to this conference from all over the world, and it turns out that Eric is doing so at the moment because he is coming in from Ireland. It's now about 9:30 in Ireland, and he told me before we started that he has not yet had a Guinness. And one thing we have to do in the center is when we're sharing results and ideas, we have to have a lot of trust in each other. And so even though Eric is not in the center, I am still going to trust him that he hasn't yet had his Guinness. At the moment, by the way, we have 220 links coming into the meeting. We've had already a fantastic selfie from Ken Hauk's lab, and I'd encourage everyone else who's in a group to send us some selfies so we can see the community that's involved in this meeting. So at this stage, I want to introduce Eric Alexanian. He's done some fantastic work related to radical chemistry as it relates to CH functionalization, getting really unusual site selectivity going against the normal trends of radical chemistry by using some really bulky reagents, and is definitely one of the leaders in this type of application. So we're delighted to have you join us today. All yours, Eric.
Okay. All right, that should do it.
That's great.
Okay. First of all, Hugh, thanks so much for the invitation today. This is a really amazing seminar series, and it's a real pleasure to be able to talk to you about some of our work in hydrocarbon functionalization over the past 6 or 7 years or so. Before I forget, I'm a whiskey drinker, so definitely Jameson, not Guinness, but I've had plenty of Jameson since I've been out here. To get started, what really motivates us, I would say the most, thinking about CH bond functionalization is, really just how far behind nature we are when we think about possibilities. So, for instance, if nature wants to synthesize Taxol in a real beautiful series of selective steps, nature's able to produce that. It's 8 different hydroxylations with oxidation states controlled along the way. And for synthetic chemists to think about doing anything like that right now, it's sort of science fiction. These are really difficult reactions to do selectively. Another reaction that nature has no problem with is CH bond halogenation. So for instance, here with this alloisoleucine derivative, if nature wants to do a primary CH bond chlorination, it's not a problem. So this alpha-ketoglutarate dependent non-heme iron enzyme can do a primary selective CH chlorination, which is then followed by an enzymatic cyclization and taking on to carnitine. So, you know, what the question that we really think about in our group is how do we get anywhere near this level of site selectivity and CH bond functionalization? And our inspiration really came from some very classical chemistry. What I think, you know, you might say is the first example of an aliphatic CH bond functionalization and synthesis. And that's the Hofmann-Leffler-Freytag reaction. So this uses a reactive heteroatom-centered radical. Okay, so starting from a bromoamine, there's a protonation, an NBR bond homolysis, followed by a 1,5 H atom abstraction and cyclization to the product there. So that's a very classical reaction, of course. Another really historic reaction was Barton's nitrite ester photolysis. So in this example, used to make aldosterone acetate from an oxygen-centered radical formed from that nitrite photolysis. But of course, in both of these reactions, the hydrogen atom transfer is a 1,5 process. So it enjoys that sort of kinetic selectivity. And that's, you know, very widely understood. And what we thought about in the group is how do we potentially think about doing these types of reactions, but in an intermolecular setting. And I think if, you know, we think about these reactive heteroatom-centered radicals, how are they going to be selective in these reactions, right? They're highly reactive. How are we going to be able to choose between different CH bonds in organic compounds? It seemed like a really big challenge. Now, it turns out that if you tune the radical appropriately, you can really get some amazing reactivity. So what we've focused on are amidyl radicals, okay? So these are bulky amidyl radicals. So there's an N-tert butyl group here. First of all, these are very easily prepared from amide, so that's great. So they're very convenient to use. And the important thing is that the parent NH bond is about 110 kcals per mole. So aliphatic CH transfers are going to be exergonic pretty much in all cases. And I'll also show you that you can get some really good site selectivity using these reagents. So we started by looking at CH bond halogenation, and this is a few years ago. I won't talk about it too much today. But we're able to functionalize a number of different compounds. We started with the bromination. So here's an example of a memantine derivative, site selective for that tertiary position. Later on, we developed a CH chlorination, and this was with my friend Chris Vanderwall at Irvine. So this reaction was used actually in the first step of the synthesis of chlorolysoclamide. So we took scalariolide, which is commercially available, and then using this chloroamide, and you could run this on 10 to 20 gram scale. It's a very easy reaction to run with just a little radical initiator. That chlorinated product was then taken on in a few steps to the natural product. And one other thing I'll point out, in all of these reactions, we use substrate as limiting reagent. So we don't have, you know, excess starting material. We don't recycle our unreacted starting material. These are all a single pass, single reaction yields. And as Hugh mentioned in the introduction, we've also started to look at getting really interesting site selectivity. I think this is one of the major areas in CH functionalization going forward, is really trying to get either catalyst controlled site selectivity or reagent dictated site selectivity. And here's just one example using artemisinin as substrate. So what we did here is we moved those CF3 groups over to the ortho positions, and what that does, it makes a much more hindered nitrogen-centered radical after that NCl bond cleavage, and now we can actually get primary site selectivity, which hadn't been done before with chemical reagents. Now it's not perfect selectivity, we have a ways to go, but you know, it's a good start and a good proof of principle, I think. One thing I'll mention, these are really easy reagents to make. So here I show you over 10 grams of the chloroamide from that artemisinin reaction. So you can really make as much of this reagent as you would want. Very easy to do. Okay, so after our halogenation chemistry, we got to a point where we wondered what was the next thing to do. And in terms of reactions, there might be 10 different groups you would want to introduce into a hydrocarbon. And instead of developing 10 different reactions, we really wanted to make one reaction that could serve as sort of a platform for other CH functionalizations. And we always kept coming back to alkyl xanthates. These are very easily transformed via radical reactions and polar reactions, and I'll show you some examples of that in a minute. And the way we did that is with a xantholamide, so shown here in the blue box. This is a yellow powder. Okay, now it's commercially available from Sigma. You can synthesize this from the chloroamide very easily with potassium ethyl xanthate. And using some blue lights, you initiate the radical chain. You make the nitrogen-centered radical, which then does the CH bond abstraction and chain transfer of the xanthate. Okay, so I won't show too many different examples here. This is work from a couple years ago, but we could functionalize natural products. And once again, we're going to functionalize the most electron-rich, sterically accessible site. So with androstenedione, it's the B-ring methylene shown there. And probably my favorite example in that paper was the functionalization of longifilines. So that alkene can be pretty problematic. So if you use something like a high valent metal oxo, it's prone to oxidation chemistry, it can do other reactions. But using our reagents, we oftentimes can get CH functionalization with things like alkenes present in the molecule. And this reaction actually worked best neat, so no solvent. So it's a radical chain process, and you'd think higher concentration is better. But you take that longifiline liquid, you put the yellow powder on it, shine blue lights, it sort of warms up, and you get 54% yield of this single product, where the hydrogen atom transfer occurred away from the quaternary centers at that accessible methylene site on the medium ring. So just very briefly, you can take the xanthate group and do quite a number of different things with this. This is beautiful work from groups like Samir Zard, Philippe Renaud, and others. So we can transform that xanthate to a vinyl group. You can do a CH amination via some polar chemistry, transform it to deuterium. One reaction we had to develop in that paper was the transformation of a xanthate to a hydroxyl group. And this is an interesting transformation because the perfect chemoselectivity of the overall process. So oftentimes CH hydroxylation can be problematic. You'll get overoxidation to the ketone. But in this case, that's controlled by the workup conditions. So with zinc, we get the hydroxylation. With MCPBA, you go chemoselectively to the ketone. We can also do trifluoromethylthioylation. And probably the simplest reaction is just to work this up with an amine, and you cleave off that xanthate group, and you take the thiol. You can do things like bioconjugation via thiolene click chemistry. And actually, it was surprising to me that the transformation of a CH bond to a thiol hadn't been done before. Okay. So switching gears just a little bit, I wanted to talk about sort of a new direction for our xantholamide chemistry, and that's in functionalizing polymers. So typically, the way this is done is using peroxide. So those will favor functionalization at tertiary positions. Okay, so in a branched polyolefin, that's going to be followed by degradation. That's usually will happen before you get addition of something like your maleic anhydride that you have in the reaction. And what we wonder is if we could use the sterically based site selectivity of our reagents to move away from that tertiary CH site, functionalize commodity polyolefins, and then do some very interesting reactions with those sorts of products. And this work was is in collaboration with Professor Frank Leifarth, my colleague at UNC. So this was published last year, and I won't spend too much time on it, but the sort of reactions that we would run is taking things like polyethylethylene and our xantholamide. You shine blue light on this, and you get a good amount of functionalization on that polymer. You can tune the amount of functionalization based on the amount of reagent that you add in. And what was an important result for us moving forward and thinking more about direct application of this, you can run the reaction with no solvent. So once again, you run it right onto the polymer and you get a good amount of xanthylation. One thing I'll point out is when you're functionalizing a polymer, you don't need that much functionalization for the reaction to be very useful. So even 4% is plenty. Okay. So recently, thinking more about commodity polyolefin functionalization, the way that you want to do this, especially in industry, is using something very different than our normal round bottom flask. So the way they like to do this is via reactive extrusion, where basically the solids are put onto this hot metal screw. It turns the reagents and then out comes the polymer. And this actually works with the xantholamide. And here's some pictures of what those instruments look like. So as you can see here, this is the functionalized isotactic polypropylene. You can see the peaks in the proton NMR shown here. This is the GPC analysis of the reaction. So what's really important is that these peaks look the same. So one of these is just the isotactic polypropylene extruded. And then our functionalized compound is that maroon peak. And you can see that the molecular weight distributions are still very similar. And looking at actual pictures of the compounds, on the left here is the extruded polypropylene. The xanthylated polypropylene has that sort of yellow tinge. This is 1% functionalized, and actually it now changes the physical properties of the polymer pretty significantly. So the functionalized polymer now adheres to glass twice as strongly as the simple polypropylene does. So that's a nice proof of principle. We're really excited about different applications of this in the future. So thinking more about small molecule functionalization and the future of trying to use these heteroatom-centered radicals, we started to think about moving beyond chain mechanisms. These are great for transferring certain functional groups, but there's always going to be some potential reactions that you might want to run that would be pretty difficult to be able to run these in a chain process. So we started to think a lot more about trying to do catalytic reactions. And our first work in this area was in collaboration with my colleague Dave Nasevich, and we developed this acridinium catalyzed CH bond functionalization shown here. So this is also using a commercially available acridinium catalyst, phosphate base, and hexafluoroisopropanol. Okay, the first reaction here that I'm going to show is the azidation. So this works with completely unactivated CH bonds. This reaction actually favors tertiary sites, so it's complementary to our chain chemistry. We can also apply this to more complex molecules as well. Okay, and what's really exciting about this approach, I think, is you can change the reaction products just by changing the trap. Okay, so this is sort of a nice platform reaction where you can access azidation products with sulfonyl azides, CH fluorination, bromination, chlorination. You can add in an activated alkene and get an alkylation product. You can also do trifluoromethylthioylation as well. So here are some examples of the sorts of things that you can do with that system. Just briefly talking about the mechanism here, we believe that this is oxidation of the phosphate base. So the excited state of the acridinium is a fairly strong oxidant. It's over 2 volts. And we think that's strong enough to oxidize the phosphate base to make an oxygen-centered radical, which then does a CH bond abstraction followed by addition to whatever your radical trap is, and final electron transfer to close the catalytic cycle. Okay, so getting back to nitrogen-centered radicals. So, you know, we always had this dream to be able to do amidyl radical chemistry catalytically. And, you know, our thoughts in this area just kept coming back to the idea of doing proton-coupled electron transfer. And, you know, the beautiful work from Rob Knowles' group has shown just how powerful this can be in synthesis. And the idea was, well, maybe we could use a simple amide and now form the amidyl radical under mild conditions. And, you know, we started to play around in this area, and then Rob Knowles and Tom Rovas at about the same time published an excellent intramolecular version of the sort of reaction we were thinking about, and those are both shown here. So in this case, it's a P set to form the nitrogen-centered radical. You get a 1,5 H atom transfer followed by addition to the trap. And actually, in Rob's paper, he reported an initial intermolecular result using 10 equivalents of substrate. So good proof of principle. Rob knew about our work trying to do intermolecular chemistry. We knew about these studies, and then we decided to form a team and collaborate and try to develop a general way of doing this sort of chemistry intermolecularly. So one of the first reactions that we tried to do is shown here. So it's a simple alkylation of THF using bisulfonyl ethylene. So we have our iridium catalyst and our base in here. And the first thing we tried was using a sulfonamide. So could we form a nitrogen-centered radical here? That NH bond is still around 103 kcals per mole. And see if we could use this to trap an alkene and deliver the CH alkylation product. And we were excited that even some of the first reactions we ran gave good results. So with one equivalent of that sulfonamide, we got a 75% yield of product. So a good start. Now, if the nitrogen-centered radical abstracts the CH, you regenerate the sulfonamide. So there's no reason you would need a full equivalent. So we started to use less and less. And the reaction yields don't drop that much. So what's the next experiment? Take the sulfonamide away, and you still get plenty of product. So it's pretty clear the sulfonamide's not doing anything in the reaction. And actually, if you lower the amount of iridium, the yield goes up even further. So the bottom line here is that the sulfonamide isn't doing anything in the reaction. So just briefly, I'll discuss the substrate scope. So we can functionalize completely unactivated aliphatic CH bonds, different heterocycles shown here. This works really well at benzylic sites. And we can use a number of different olefins to trap. So it's not limited to bisulfonyl ethylene. Here are a few different ones shown here. It just has to be an activated alkene for that trapping step. And we've also started to apply this to more complex molecules. So here's an alkylation of the activated position here in ambroxide. Here's our memantine derivative again. We get good selectivity with benzylic, between different benzylic sites as shown here. So with ibuprofen, we get a single product. And with this pyrimidine-containing compound, we also get a single benzylic functionalization. So the real question for us was, what is the mechanism of the reaction? So initially we thought, well, maybe we're forming some small amount of radical, and this is just a simple chain process where the catalyst isn't doing anything at all. So we tried to do some control experiments where you add in radical initiators. We didn't see any product. And the more straightforward experiment is to measure the quantum yield. The quantum yield of the reaction is very low, so it's just not consistent at all with the chain process. You take away the iridium, you get no product. You take away the phosphate base, you also get no product. So if we compare the site selectivity of this alkylation to the selectivity using the acridinium system, so the work that the Nisevich group did with us, the site selectivities are very different. So with the acridinium, if this is a phosphate oxidation and you get a 1-to-1 mixture of products here, and with this iridium phosphate system, you only see a single product. It's just not consistent with phosphate oxidation playing a major role in this iridium chemistry. So what sort of led us down the ultimate path to getting to where we are today, we thought a lot about this interesting coordination of the iridium catalyst and the phosphate base. So Rob's group had shown this previously. The phosphate base coordinates to the CH bonds in that ligand system. Those are relatively acidic sites. You can see with this NMR titration, the movement of that peak, and you can pull out an equilibrium constant, which is about 1 × 10⁴. So this is a strong coordination between the phosphate and the catalyst. The job plot also indicates that this is a 1-to-1 coordination of the phosphate base and the catalyst. And Rob's group actually obtained this beautiful crystal structure of the iridium system bound to the phosphate base, and you can see the interaction right here. So nice evidence of that coordination as well. Okay, so this is just another one of the standard reactions that we looked at. And we started to question if that CH bond interaction is so important to this chemistry, what if we replace CH with CF? Very similar size, would completely disrupt this coordination. So if that's the case, we should make the fluorinated catalyst and the reaction should totally shut off. And that's what we see. A major difference between these two catalysts. And then just to make sure that we didn't synthesize some really poor catalysts, we applied it to one of the many reactions from the Knowles group, showing how useful these catalysts can be, and the fluorinated catalyst worked just fine in this cyclization reaction. So it is an active catalyst for proton-coupled electron transfer, but just not in this particular system. Okay, so this is the last chemistry slide. And it summarizes quite a bit of work. So it took us about a year to really get a handle on what we think is going on in the reaction. So what we ended up doing is looking at some time-resolved photoluminescence as well as transient absorption spectroscopy to try to see what's happening when the excited state of the catalyst is quenched. So over here on the left, what this shows is that without phosphate and without substrate, the iridium-3 does not form iridium-2. So that would be the sort of green and blue and purple line here down at the bottom. So this, in the y-axis here, shows increasing iridium-2 concentration. However, when the iridium is in there with the base and the substrate, so ethylbenzene was just a representative substrate here, that's when you start to see iridium-2. So it requires your CH substrate to be in there in order to see the iridium-2. And then with more substrate, you see even more iridium-2. And then to prove that this, or to get some good evidence that that CH bond cleavage is involved directly in the electron transfer, we looked at ethylbenzene and deuteroethylbenzene using some time-resolved photoluminescence studies, and you can see here that there's a quenching KIE. So the quenching of the excited state involves that CH bond cleavage step directly in the electron transfer event. Okay, so our best mechanistic hypothesis at this point is that this complex is excited to give a photoexcited complex, which then participates in a CH bond p-set reaction. Okay. So typically, proton-coupled electron transfer uses relatively acidic bonds, such as NH bonds, right? Where the base can bind. There's no way that the phosphate base is going to bind to a CH bond, especially not in an intermolecular way at any appreciable amount. But we think it's because this complex forms and you can bind to that CH bond as the electron moves, that this is basically a CH p-set reaction. And we think this is potentially a new elementary step for CH bond abstraction. That's then followed by addition to the alkene and electron transfer, proton transfer to get to the product. So we're really excited about this reactivity. There's a lot of different directions where we're taking this synthetically. There's also a lot of questions that we're still trying to answer going forward as well about mechanism and other things like that. But really exciting stuff and very unexpected when we started the project for sure. Okay, all that's left for me to do is to thank my group. I've really been blessed with an amazing group of coworkers at UNC. I've listed the students that have been responsible sort of throughout the talk. Also, Frank, Leifart's group, it's really been an excellent collaboration starting our polymer work there, and it's also been an amazing time working with Rob over at Princeton and his group. And there's a lot of really interesting results that those collaborations have led us to, and that's been a lot of fun. So I'll stop there. I'm happy to answer any questions. And once again, Hugh, thanks so much for the invitation today.
Eric, wonderful talk. Time's running a bit late, so I just want to make one comment. It's amazing that last part of your work where you've got that new mechanism for the photoredox possibility for CH functionalization. I think that's a fantastic result. Congratulations on that. That can develop very, very nicely.
Thank you.
I also want to congratulate you on how you've demonstrated the importance of collaborative research, because obviously, you had a fantastic foundation in what you were doing in radical induced CH functionalization, but you demonstrate the ability to collaborate beyond that with other synthetic organic chemists, and that's really a fantastic accomplishment as well.
Yeah.
Something that we strive for in the center, but you're clearly doing it yourselves. Well done.
Yeah, thank you so much. Yeah, absolutely. So much of this work never would have been possible without Frank and his group, as well as Rob and his group. It's been a real pleasure. And it just makes chemistry a lot more fun and exciting, I think, too.
We couldn't agree more with you. Okay, thanks very much. Okay, so our last speaker is Francis Arnold. And Francis, sorry for keeping you waiting so long. Actually, believe it or not, Francis was the first one to sign into the Zoom today to be ready for this talk. So it's great to have you involved in this. Obviously, your schedule is very busy, so we really appreciate having you having the time to join us. Obviously, Francis, with her fantastic achievements in vitro enzyme evolution, has really sort of totally revolutionized this field. But in addition to that, over the last year or so, she and her group have really got some absolutely fantastic applications related to CH functionalization, where they're getting these enzymes not just to do unusual selectivity, but actually the types of reactions that aren't even known in nature. So we're really looking forward to hearing your presentation now.
Thanks, Hugh. And I signed on early because I wanted to hear all the great talks before me, Richmond's and Eric's, because we get our inspiration from what human chemists do. I haven't met this community before. I've never talked in this forum before, so I want to introduce what we're interested in. And since it's such a short talk, I'll just mainly talk about the work of In-Ha Cho, Zhizhen Zhang, and Yang Yang, but I'll fit in a few extra things as well. For those who don't know me, I engineer enzymes to do things they wouldn't normally do. And we think of the engineering method that we use, which is based on evolution, as really a molecular optimization problem, where you're optimizing the actual DNA code for an enzyme to solve a problem that's defined by me. I am the breeder of molecules. And we don't know what this optimization landscape looks like. At least we didn't back when we started developing these methods in the late 1980s. But you can argue that it's really got to be more smooth like this than rugged. Otherwise, we wouldn't be here to talk about it. In other words, we are the products of evolution reaching all the way back 3 billion years. And if fitness weren't in some way evolving on a smooth landscape where the steps you can make, this is actually very multi-dimensional, because each step is a way you can make a mutation to a protein. But if mutations always sent you into crevasses of non-function, we would not evolve. So I, in a nutshell, got the Nobel Prize for recognizing that this landscape must be smooth in some of its many dimensions, and therefore one could develop experimental techniques to exploit this. And it's really very, very simple. You can take a random uphill walk for the optimization, starting with the gift of nature, right? The natural enzymes, a huge diversity on a silver platter, 3 billion years of work. You could take a gene for that, make a small number of mutations. Cells translate those into mutant enzymes. And here comes the hard part for the human being, which is to screen for things that you are interested in. Most mutations are deleterious, sending you to the trash can in the old days. Now they go into machine learning algorithms. We'll see how big a better trash can that is. But if you've defined the problem well and you have good analytical methods, you can find in a really screening only a few hundred clones, you can find beneficial mutations, feed that back into the process and iterate as you climb up this fitness landscape and make a better enzyme. So that essentially got me a very nice trip to Stockholm in December, because lots of people use this method. And by the way, if you ever get invited to that party, I do recommend that you go. It's a really good party, and I tell that to my friends who have a chance to experience that. What's exciting about evolution, and what I want to talk to this group about today, is that we can go where nature has never gone. Now, we can start doing chemistry, for example, that was invented by human beings. Imagine that. Everybody says, well, I'm inspired by nature. Well, on the other hand, we should also be inspired by the creativity of human beings, because in the space of all possibilities, which is bigger than all the particles in the universe by far, all the sequences that are relevant to the biological world and that nature has explored going all the way back to the last universal common ancestor is just the tiniest fraction of the possibilities. And that's true for the functional possibilities as well. There's a limited set of functional transformations. It's very big, but it's still limited in the biological world, whereas chemists have a number of transformations that biology hasn't explored. And so I want to talk about how we can bring those worlds together and use evolution as a way to go into the future. Now, humans have been doing this for a very long time. Let's see if I can go forward. That's a good thing. We've been modifying the biological world using evolution. We didn't know it was evolution, but basically evolution by artificial selection to create everything from corn to carrier pigeons, lab rats, racehorses. We've been making all sorts of things that are useful to human beings, that give us comfort, that feed us, that are not remotely natural. This, for example, would be eaten in my neighborhood. Coyotes would find that a delicious piece of coyote food. And so we have been able to do this for thousands of years, making these things without really understanding the underlying physics or chemistry. So it's something quite powerful. And basically what I do is I breed molecules like you can breed cats and dogs. So with that introduction, I want to move to the same inspiration that Eric presented, that nature's figured out how to do CH functionalization, does it really very well, and the P450s are remarkable examples of that. This is one of nature's most versatile catalysts. It's an iron heme enzyme that generates and uses its reactive iron oxocation radical intermediate. It's compound 1 for selective functionalization. And with the help of the protein coat, which is evolvable, it can do this with high activity under mild conditions and extremely good selectivity. And that's, as Eric mentioned, that's what's so impressive about the biological world. It's found all over the biological world, and in fact, humans have collected the sequences of these. So by now, we know hundreds of thousands of cytochrome P450s that modify a vast array of different substrates, and I'll come back to that. Now, we recognized the similarities between compound 1 and other reactive species known well to synthetic chemistry in human-invented chemistry, in particular small molecule catalysis, transition catalysis involving carbines and nitrines. And as you know, there's a rich literature on carbene and nitrine chemistry in all sorts of journals going back a number of decades. And this literature apparently has not been read by nature, because she doesn't, as far as we know, have carbene transferase activities. There's no carbene transferase activity in the databases. And only just now, as a result of our work, are people starting to find that nature may do nitrine transfer activity. But we invented them before they were discovered. I'm going to talk about a P411 in this talk, in which we have removed the axial cysteine and replaced it with a serine. And we did that for a very particular reason that it's not important before. But basically, this enables function inside of living cells. You can get to the active iron 2 state inside of living cells with a weak reductant. That's the endogenous reductant. Turns out the P411 is a really interesting family. There's no P411s known functional cytochrome P450s. That abolishes the native monooxygenase activity, but it confers, surprisingly, very high activity for carbene and nitrine transfer. So all of the proteins that I'll tell you about are P411s. And I am the mother of this enzyme family. It's a non-natural family, but it's fully genetically encoded, and it does some pretty cool chemistry. So now let's take a minute to think about this. I know that some of you in the audience, you may be uncomfortable with the idea of using bacteria in chemical synthesis, but if you've got a selectivity problem in synthetic chemistry, you ought to consider biology as the actual solution. And if it makes you uncomfortable with squishy things like proteins, and that makes you queasy to think about it, just think of a protein as a self-assembling, DNA-encoded chiral metal complex whose structure and properties can be tuned by evolution. In other words, you can make 1 million ligands in an afternoon, and then if you can search through those, you can find things and use evolution to do the fine-tuning of the reactivity. So let me jump into some of the recent, I'm not going to go through ancient history here, but I want to share some very recent results. For example, we used this directed evolution to explore all sorts of new chemistry that reactive intermediates, like the carbines and nitrines, when you form them in an enzyme active site, that they can participate in. And once you find those activities, you can use this reliable optimization strategy to create useful catalysts. So one particularly challenging CH functionalization reaction we recently tackled, actually we've been working on it for some years, but we published it recently, is carbene insertion into CH bonds to make new carbon-carbon bonds. And once again, nature does not use this mechanism to make carbon-carbon bonds. And in fact, no one has found these carbene transferases at all in the biological world. And furthermore, some human chemists questioned whether an iron heme protein system could do this at all. And you may be aware, for example, the work of Doug Clark and John Hartwig's groups, who inserted iridium hemes into proteins and showed those would do CH insertion. But I'm going to share with you a long, hard slog that Kelly Zhang did, starting with very low levels of discovered activity. So she found a P411 that gave just a few turnovers for carbene insertion, and over multiple generations, she was able to coax a significant amount of activity out of that enzyme, showing that in fact, fully genetically encoded proteins can do that using earth-abundant iron. And she was able to give E. coli the ability to alkylate a range of benzylic and allylic CH bonds with high activity and selectivity, so that this paper published at the beginning of the year actually gave biology, I think it was interesting because it gave biology a whole new carbon-carbon bond forming mechanism. There aren't that many in the biological world. So here was a mechanism invented by humans and now genetically encoded. It's also a pretty good catalyst compared to any other chemical catalyst because you get very good selectivities in many of reactions and reasonable turnover numbers. And we're still working on that. Now, once we had carbene insertion possible, Zhangyi Wang, whom some of you know, then asked whether he could do something quite useful with this carbene transfer and convince enzymes to use fluorinated carbenes for late-stage alkylation. And catalysts that can use this acceptor-only type carbene precursor for an enantioselective alkylation have not been reported. And because the electron donating group is usually required to attenuate the very high reactivity in carbene intermediates and give the stereo control of CH functionalization. But we've shown that enzymes can stabilize some pretty highly reactive intermediates, and Zhangyi Wang, working with Jun'er Zhang, just recently published fluoroalkylation at positions, carbons alpha to a nitrogen. So we just heard some interesting chemistry along those lines from Eric. Here's a carbene transfer mechanism that can do that using variants of P411. And these are, as you heard, interesting substances because this position alpha to the nitrogen is often metabolically labile and it's prevalent in drugs. So you'd like to be able to do modifications there. And the introduction of fluoroalkyl groups could be quite interesting. So Jun'er and Zhangyi found in Kelly's lineage an enzyme that had very poor selectivity, but at least some activity for this. And over several generations of evolution, they were able to create P411 PFA. And I'm not doing any of the protein engineering in this talk, but they were able to make this catalyst that will fluoroalkylate here with 98% EE. So all done in water using atom economic carbene precursors for that. And it has quite a reasonable scope. So you can, once again, it's in room temperature and water. You can fluoroalkylate substrates that have, for example, aldehydes or halogens. So it's tolerant of these functional groups. You can even get primary fluoroalkylation and with reasonable turnovers, and you can evolve it for the selectivity. We just stopped because it takes some work to do that, and we just demonstrated that this one catalyst can do all these different reactions. Furthermore, you can take other carbene precursors and do the perfluoroalkylation, in this case, with the same enzyme, so it'll accept other carbene precursors, and then you get even higher selectivities and also still some reasonable turnovers. And just to demonstrate the evolvability of the system, and this is really the power of using biological catalysts, is that you can fine tune them so that one set of catalysts, for example, will do the, will make one enantiomer, and another set of catalysts with a different set of mutations will make the opposite enantiomer. So you can do these divergent, stereodivergent reactions as well. It's a tremendous level of control. And I mentioned that there are so many P450s in the protein database because I want you to think about this as a possibility for a general platform for late stage alkylation, that you could take a cytochrome P450 evolved in nature that site selectively hydroxylates a compound, and now with directed evolution, or even just putting in the serine mutation, which activates it for these carbene transfer reactions, you could now convert it into these enzymes into late stage alkylation catalysts. That's what we're working on to prove right now. But I promised you in this talk with the title that I'd tell you about some of the hottest things happening with nitrine. So let me move on to that. I apologize for the long-winded introduction with carbene transfer, but all the principles, at least the protein engineering principles, remain the same. And let me take you back to just a little bit of the ancient 2013, 2014 evolutionary history, because there, Todd Heister and John McIntosh, who were postdocs in my lab at the time, showed that, yes, the P411 can do intramolecular CH amination with appropriate sulfonyl azides, and that unsurprisingly, it was easy to find an enzyme that will target the benzylic position. So some set of mutations can give you primarily the 5-membered ring for this reaction. But what's so cool about this is that you can evolve the enzyme to go after, with very high selectivity, the bond right next door that is significantly stronger than your benzylic CH bond. And that, back in those early days of 2014, gave us a good feeling that evolution would be able to take us where human chemistry, especially with small molecules, is going to have a hard time going. Now, after the intramolecular CH amination, we did a number of intermolecular nitrine transfer examples. We showed sulfimidation 2014, aziridination, once again making different enantiomers based on your tunability. We published intermolecular amination in 2017, and I should note that Rudy Fazan's lab has also done a number of really nice examples using P450s as well. So this idea that intermolecular nitrine transfer was a possibility came after the initial work. But let me jump right into the most recent work. The recent work of Zhijun Jia and In-Ha Cho, because it's really quite spectacular, and I won't bore you with all their evolutionary history, but it basically comes from having a great collection of evolved enzymes in the laboratory that previous workers had done. And we took something that Chris Pryor had done, a P411 that he used for a sulfimidation rearrangement reaction, and then that passed through the hands of a couple of other talented students who did it for crazy things like making bicyclobutanes by 2 carbene transfers, until In-Ha and Zhijun got a hold of it, and they wanted to solve a couple of problems, one of which is the use of the tosyl azide, the tosyl protecting group. That tosyl group can be difficult to remove, and we always ran into griping from reviewers about having that there. So it would be nice to move away from that to other nitrine precursors. And we also wanted to move to something that would be very easy to handle at large scale, because these enzymes really are synthetically very useful and should be part of the toolbox of synthetic chemists. So here, they therefore tried acyl-protected hydroxymates, which would yield carbonyl nitrines that upon intramolecular CH amidation would make these lactams. And this chemistry is unprecedented in the catalytic literature. There's nothing like it, and there's certainly nothing like it in the biochemical literature. This is not known. That doesn't mean that it doesn't exist in the biological world, but no one has reported anything like that. And one reason it may be elusive, and certainly the reason it's elusive to small molecule catalysts, is that the CH amidation is competing with a Curtius type rearrangement, which is very facile, and hydrolysis takes you to the amine. And that's a problem with the chemical catalyst. With the enzyme, we have a reductase domain on some of these, and you get the amine just by direct reduction of the nitrine. So these are your dominant reactions. But in my world, that's not a problem as long as you can find a little bit of your desired chemistry. So the desired reaction would be this intramolecular CH amidation. And they, Inha and Zhizhen, found an enzyme with 1% yield for that. And in my world, that's finding gold. Because once you find 1% yield, then you trust evolution to solve the selectivity issue. And you can do that. So they evolved it over just a few generations. It already had very high enantioselectivity. So this is the evolution of enantioselectivity. This is the evolution of the total turnover number. So it's very small for turnover to the product lactam, but that could be improved over several generations. And they ended up, and this is what's really quite remarkable, they ended up using these simple acyl-protected hydroxymates, and they ended up with an enzyme that had, let's see if I don't have it here, it's over 1 million turnovers, 1 million. So basically you can make as much of your product as you want. And not only that, in the beta-lactam version of the enzyme has a broad substrate scope, so all of these things were made. And I want you synthetic chemists to truly appreciate this ease with which these things can be synthesized. You take your cell lysate, mix it with your substrate in water or a buffer at room temperature, and then go away for the weekend. And you come back and your product has precipitated out, you filter it, and it's 92% pure by HPLC. So that is your synthesis when you can convince the enzyme to do all the hard work. They didn't stop there. For one, so we have this enzyme that we started with something that can make the 4-membered ring, but you can tune it now. So they made different versions of the enzyme that primarily make the 5-membered ring, and you can also tune it to make the 6-membered ring. So you have something with very good selectivity in terms of ring size, in terms of enantioselectivity, and it's all tunable by evolution. So you can take a substrate like this with all these different possible sites for reaction and tune the enzyme to choose them, overruling any kind of inherent bond reactivities of the system. So let me end with one last short story that comes from postdoc Yang, who set his sights on one of the most challenging problems in asymmetric amination. And that's a field he knows well from his PhD in the Steve Buchwald lab. And Yang reasoned that he could make chiral diamines in an intramolecular amination reaction controlled by the enzyme. So taking this, getting back to the sulfonyl azide type precursors, he found mutations in the P411 active site that could give you this intramolecular amination directly and very efficiently to the benzoic bond with essentially perfect enantioselectivity. We can't find any other product, and 72,000 turnovers. So that was, he got that quite quickly. But the thing about evolution is you can keep challenging it. So the next thing he did was evolve his diane-1 catalyst for unactivated secondary CH bond amination. And he quickly generated catalysts that can make either enantiomer of the protected diamine. So here you got one. So you're going to go there. You can make this guy with one catalyst, and you can just turn around and do a couple of generations. So a single mutation at position 327 gave you a catalyst that makes this. Just proof of principle to show it can be done. But if you're Yang, you don't stop there. So now here's a fun one. Imagine the enzyme can take, so I skipped one thing. For one thing, Diane with a proline. So now instead of a threonine at this position, you take a proline. Yang found that that could desymmetrize this gem dimethyl substituted carbon and make your quaternary stereocenter with 99% E. So the enzyme is able to do this with great activity and turnover. But don't stop there. He went on to show, he said, oh, wouldn't it be really wonderful if you could take a racemic substrate? So now the enzyme has to accept both substrate enantiomers and perform an enantioconvergent transformation on that to give you not only the tetra substituted stereocenter, but one version of that. So you're taking a mixture of enantiomers and you're converting it 100% into your desired product. And those are, as you know, those are hard to do, but he was able to train the enzyme to do that with the methyl phenyl substitutions. And then he said, well, do you think that enzyme could learn to do what's almost impossible for chemists to do? And that is set this stereochemistry with an ethyl-methyl substitution. So you take the methyl-ethyl racemic, and he can now make the methyl-ethyl substituted stereocenter in a single step with the enzyme. So that is, I think what we've learned is Yang is very smart, but enzymes are even smarter. Enzymes can learn very quickly, and they can do things that human chemists find extremely challenging to do. So with that, I'm going to quit and just point out that we've made these enzymes do all sorts of different things. They bring together human chemistry and powerful biological design processes. And this is all work done by human beings directing the evolution using the brilliant power of evolution.
Francis, that's a lovely talk, and it's amazing that the work is going faster and faster. It's amazing what you've been able to achieve in these enzymes too. Unfortunately, with the questions, our chat room's not working properly, but there is one question I have for you that's come in, and that is, so obviously you've demonstrated the power of evolving the enzymes to get the activity you need, but in the process, obviously, there's a lot of negative results too, because many of them are doing worse. So there's an opportunity, maybe an opportunity for really massive machine learning here to help to really understand how the enzymes, the ways that one needs to evolve, as well as the powerful tool of the evolution. Do you bring that into your research as well?
Yes, we've been doing machine learning since 2012. We use all of the data from many of our evolution campaigns to predict how best to make the next generation. The chemists have moved so fast with these enzymes, they haven't waited for the data-guided evolution. And it's been so easy to do many of these things. But that's where the future is to combine data-driven evolution to get you there faster.
Right.
So people, actually, I'm on Twitter. A lot of people are on Twitter. On Twitter, you can find a lot of tweets by me and Kevin Yang on machine learning and protein engineering.
Okay, great. But once again, thank you for a really spectacular talk, and also let's thank the other two speakers. It's really been a tour de force covering many aspects of CH functionalization from strategy to methodology, was the small reagents to now this fantastic talk to finish off with this enzyme evolution. So once again, please join me to thank all the speakers.